Hi everyone, welcome back to our seminar. Today Shaun Fallat is going to talk about graphs that admit orthogonal matrices.
Thank you for that introduction, and thanks everyone for attending. I hope I can give you some recent insights that we've had concerning this problem. Okay, so this is the plan. It's rather long-winded, but I'll go through it as best I can. Hopefully, I can keep you folks interested. So let me just begin with the sort of broad introduction. So the question that sort of I'm dealing with today is very straightforward. So there's a graph you see on your screen. Hopefully you can see my cursor, very simple graph. And the question I'm asking is just, does this graph describe a pattern of a 4x4 symmetric orthogonal matrix? The symmetry part is just so I can keep things in the context of graph theory. And you think about it for a while, and then you might come up with an example that looks like this. So the answer is yes to this question. I mean, not very interesting, I suppose, at this moment. But this is kind of the question that I'm asking. You're handed a graph, and I just want to know, is there an orthogonal matrix that somehow respects that graph? Okay, so before I sort of thought about this lecture, I thought I should go back and have a look at other people's works when this kind of question was asked before. And so I phrased this sort of literature review as other work on sparse orthogonal matrices. And so I'm certainly not claiming that this review is comprehensive. It's just sort of what I was able to sort of figure out in the last month or so. Fiedler, a lot of things start with Fiedler, I suppose, in basic combinatorial matrix theory. Fiedler conjectured that if you take a square, fully indecomposable orthogonal matrix, it has to have at least 4n minus 2 non-zero entries. So this is a lower bound on the number of possible non-zero entries associated with an orthogonal matrix. Its symmetry is not imposed here. It's just a matter of just whether entries are zero or not. This was proved 2 years later, as you see, by Beasley, Beraldi, and Shader. And later, Shader, you can read in the Rocky Mountain Journal, a really interesting paper where he gives a kind of a slick little proof, another proof beyond what they had done in the 93 paper. There's this really cool product, I suppose you want to call it, weaving, that Rob Cragen, the first I saw of it was in Rob Cragen's paper, where he used this concept of weaving to generate in the paper that I read, weighing matrices, right? And you can use this. You can use this sort of product later also to generate different kinds of orthogonal matrices. Shaun and Shader in 1999, they sort of expanded this idea that Fiedler had and sort of determined the fewest number of non-zero entries in a fully indecomposable row orthogonal matrix. So here you're not necessarily requiring things to be square, and you're just looking in sort of orthogonality in one kind of direction. You can see in that same year there was another paper on fully indecomposable orthogonal matrices, where you fix the number of zero entries and you ask if you can sort of describe an orthogonal matrix, that doesn't have too many zero blocks, and you can do that whenever the number of zero entries is constrained in this regard. Further in 99 again, you see the weaving process reappear, and Chiang used it to generate other kinds of orthogonal matrices with the fewest number of non-zero entries. Later in 03, different kinds of patterns started to appear, and in this case, you were restricting yourself to having one row or column that had all non-zero entries. I just call that totally non-zero. And in that case, they determined the fewest number of non-zeros. And then I sort of add in in 2013, the paper that the authors described as sort of the part of the discrete math research group here. I mean, we weren't the first to ask this question, but I mean, we sort of investigated this, where you're restricting to symmetric matrices when you sort of asking them to admit orthogonal. And we noted a bunch of examples and proved a few results. I'll say some of those later on, about the complete graph, the complete bipartite graph when the parts are the same, and so on. And that diamond graph that I had at the very beginning that I mentioned, actually that appeared in an earlier paper in 2002 by Duarte and Johnson, where they were actually asking questions about fewest number of eigenvalues of a graph. So the next and last thing that I'll mention is that there's this nice note by Bailey and Cragen again. So this is Rob Bailey and Rob Cragen, where they actually investigated, in this case, symmetric, I'll mention orthogonal matrices, where they required the main diagonal entry to be 0 and all the off diagonal entries to be non-zero. And they referred to this class as OMZD. And they sort of proved, among many things, but they proved when such, for what values of n such OMZD matrices exist. So that was kind of a crash course, if you will, just on people worried about patterns of orthogonal matrices. For me and for the remainder of this talk, the idea is going to be a graph is you're given a graph, just a simple graph, and I'm going to associate a class of symmetric matrices to that graph, and then I'm going to ask, what about the eigenvalues associated with those symmetric matrices? And so given the graph G, the symmetric matrices that I'm interested in are the class S of G, which you see here, where the non-zero off-diagonal entries are constrained by the adjacencies of the graph. And I impose no conditions on the main diagonal entries. I mentioned here quickly, it comes up a little bit in this world, but not so much. But I mean, folks might be interested. The positive semi-definite matrices that sit inside this class S of G are of interest, and sometimes play a role, particularly with Q of G equal to 2. And of course, for those of you that are sort of more interested in things like the adjacency matrix or the Laplacian or the signless Laplacian or the normalized Laplacian or all that kind of stuff, the class S of G I've just described, of course, includes all those matrices and obviously much, much more. And so just again, another picture of a graph where I just sort of highlight the possible matrix that belongs in this class S of G, where G is the graph above. So it just gives you a sense of the kind of matrices that we'll be dealing with. And one of the big problems out there, I suppose, in this arena is the inverse eigenvalue problem of a graph, where you're handed a graph, and then you want to ask yourself, what are all the possible eigenvalues that are realized by the class S of G? And somehow you want to be able to determine that list of spectrum without, explicitly writing down all the spectrum and all the matrices naturally. I'll just say here quickly that in a couple of obvious cases, if the only graph that realizes a single eigenvalue, of course, is the graph that has no edges, because you're only playing with scalar matrices. And on the flip side, the complement, if the graph is complete, then the inverse eigenvalue problem is solved. And basically you can realize any list of n numbers you want for the complete graph, as long as there's at least 2 in the collection. I bring this up because it does play a role. Fiedler's, I labeled it as Fiedler's tridiagonal matrix theorem. Basically, what this theorem is saying is that the only matrix that upon diagonal perturbation keeps the rank high, that is the rank of A plus D for D any diagonal perturbation, is at least n minus 1, that the only matrix that has that property, roughly speaking, is the tridiagonal matrix and the full tridiagonal matrix. And so, of course, that's subject to permutation, but roughly speaking, the only such matrix that works is the tridiagonal. And of course, the only graph that has a tridiagonal matrix pattern is the so-called path. And so one of the consequences of this result is you're basically saying that the spectrum, the multiplicity of any eigenvalue, can't be more than 1. And of course, the multiplicity of n eigenvalue is at least 1. So then the multiplicity of every eigenvalue is precisely 1. And you can go in the other direction. So every path can only allow simple eigenvalues. And to go in the other direction, you can show that any list of simple eigenvalues can be realized as the spectrum of some tridiagonal matrix. And so we've, in some regard, characterized we've resolved the inverse eigenvalue problem for paths. Now, the case of distinct spectrum is interesting and sort of is something to think about. So Duarte, maybe I'm forgetting now, in the early 90s, sort of extended this idea that he said, look, any collection of distinct eigenvalues can be realized by any tree, not just a path. And so he extended Fiedler's result. This is not if and only if, of course. He just says if you're handed n distinct numbers and you're handed a tree, then you can find a matrix whose pattern respects that tree that has those eigenvalues. And then more recently, Monfred and Shader actually extended Duarte's idea to any connected graph. That the fact that the graph was a tree was not that important. So if you're handed n distinct numbers, you can realize those numbers as the eigenvalues of some matrix associated to any connected graph you want. On the same number of vertices as the list of numbers, of course. All right. The parameter Q, I've made reference to it a couple times. So here's what we're going to talk about today. So for a square matrix, Q of that matrix just designates the number of distinct eigenvalues of the matrix A. And then you can push this notion towards what we call the minimum number of distinct eigenvalues of a graph. And that is this parameter Q of G, where I simply minimize the Q of A, where A ranges across all matrices in S of G. So I calculate the minimum number of distinct eigenvalues of every matrix in S of G, and I take the minimum of that, and I simply call that Q of G. And so I'm interested in studying this number Q of G for a fixed graph G. And of course, you start to sort of think about things for a minute. Q, of course, ranges between 1 and n, where n is the number of vertices in the graph. And if Q is 1, that means there's only one eigenvalue. And of course, that means the graph has no edges, something we described a moment ago. And on the other hand, if Q is n, then that means all the eigenvalues have multiplicity 1. That is, they're all simple. And furthermore, and this is true over all matrices in that class, which means that the largest possible nullity, even though I haven't formally defined that, the largest possible multiplicity, is 1. And the only graph that has this property where all the eigenvalues are required to have multiplicity 1 is the path. We just saw that. Fiedler's result sort of gives that to us. So that's just another way to recast Fiedler's theorem, if you will. Now, if you've studied the adjacency matrix at some point in a course, or read any book on basic combinatorial matrix theory, when you read about the adjacency matrix, one of the things that pops up right away is you can determine a bound on the number of distinct eigenvalues of the adjacency matrix in terms of the diameter, and that this is the result here, classical statement that the number of distinct eigenvalues of the adjacency matrix is at least the diameter plus 1. And I just write here a couple of bullets, not that I need to educate you folks on it, but I'm just sort of giving you a hint that the proof just uses the concept of the degree of the minimal polynomial. And I should say that the proof doesn't actually use, that the entries are 0 and 1. It uses more about just the patterns of not only A, but the powers of A. And of course, the proof that you read in any basic book applies to any entry-wise non-negative matrix associated to the class S of G. It doesn't really have anything to do with zeros and ones. I mean, zeros and ones makes it more convenient because you can talk about walks and such, but it's not really that important. And so you can ask yourself, okay, so now moving away from the adjacency matrix, is there still a connection between Q and the diameter? And in short, the answer is no, but that's actually a bit of a white lie. I mean, there certainly is some kind of relationship. It's just not so direct like it was in the context of the adjacency matrix. So if you want a result like the one associated with the adjacency matrix, then what you have to do now is you have to add this extra little wrinkle here, so that not only are you worried about the diameter, and then you sort of have this bound between the number of distinct eigenvalues and the diameter plus one, but somehow whenever that whenever that shortest path is sort of achieved, there was only one way to obtain that shortest path. Because as soon as there's another way to do it, then you can rig these matrices so that there could be weird cancellation in those sequence of powers that you sort of generate. And so it's not clear anymore that you can ensure that the degree of the minimal polynomial is somehow, depends on the length of that path. When the entries were non-negative, there's no way to rig it so that you get these weird cancellations, but certainly you can do that. However, if you go back and you say, okay, suppose the graph is a tree, then it turns out that you can't rig things. I mean, partly because things are unique here, but also because the entries, you can assume the entries are non-negative if you want. Otherwise, you could make them non-negative using signature similarity. And so you get this diameter bound, just like you did in the context of the adjacency matrix. And sort of roughly speaking, that's kind of where it stops, if you will. But by that I mean is that once you move beyond trees and so forth, you don't really necessarily have any direct relationship in this regard. And I should say, and I'll say a bit more in a slide, that the equality need not hold, right? It can be very bad for trees. And just on the other side, if you take the hypercube Qn, you have these two consequences. So here's a situation where you can design things for a matrix associated with the hypercube so that the number of eigenvalues is very small, but of course the diameter sort of grows, if you will, as the number of vertices grows. And so, okay, so there's a situation where things become interesting. And of course, the Q equals 2 case is something I'm going to focus on. All right, so going back to the trees, just so I can close this discussion, we know that the Q of t is bounded below by the diameter plus 1, and if the diameter is at most 5, then in fact it's known that equality holds. And for diameter 6, it starts to go in the wrong direction. What I mean is that there are trees for which there's a strict gap between Q and the diameter plus 1, and here's one of them. And then, of course, once you find one, then you see what you need to do in order to grow and make the gap, roughly speaking, as big as you wish as the number of vertices grows. And that was done by Kim and Shader in 2013. Okay, I mentioned that, Q equal to 1, Q equal to n, those are sort of done. And I put this theorem up here because I just want to highlight that, roughly speaking, this is the last value of Q that we have completely characterized. Q equals 1 is done, n is done, and this is the last one. So Q equals, roughly speaking, the number of vertices minus 1. We have a theorem. We characterize those graphs. Now, the way I write the theorem here, which was proved in 2017 from a Burrs focused research group, it's written in this way because that's how the sort of proof kind of went along. But roughly speaking, if you consider connected graphs, the only two that are sort of pop up are items C and D. Right? The path has Q equal to n. We already talked about that. If you take the union of two graphs, it's not difficult to keep a track of what Q is. And of course, the two new graphs are these ones, where you take a path and you just drop a leaf off somewhere in the interior because you don't want to drop it off on the end. Or you take a path and you sort of draw a little triangle on the bottom of that path and you slide that triangle back and forth. And those guys are the only two graphs that have only two connected graphs, that have Q equal to this number of vertices minus 1. And then after that, I mean, we really don't have a lot of, we do not have an official characterization of any other Q value as to the best of my knowledge. Okay, so today the title of my talk was Graphs that Admit Orthogonal Matrices. And so I claim that those are the same as studying graphs that have this Q value precisely equal to 2. And I remember in that discrete math research group in 2012 or 11, whenever it was, and one of the graduate students in that group said, "Oh, we should study the graphs with Q equal 2." And I remember thinking to myself, "Sure, I mean, that can't be too hard." I couldn't have been more wrong. well, I should be careful about that. I mean, it's just that I haven't sorted it out yet. I mean, maybe someone else can. But so the first observation that you can sort out for yourself quickly is that if S of G does contain or does admit an symmetric orthogonal matrix, then that's the same as saying that Q of G is equal to 2. And of course, if there is an orthogonal matrix, the eigenvalues are 1 and -1. So you agree that the graph has Q equal to 2. And secondly, if the graph has Q equal to 2 and you identify these two distinct eigenvalues, then you can scale and translate and wiggle around to force those two numbers to be -1 and 1, and yet stay inside the class S of G. So that truly is just basic arithmetic. Another way to say that the graph has 2 eigenvalues is to say the minimal polynomial has degree 2, which is the same as saying there's a way to write the second power of A in terms of a linear combination of A and I. And on the face of it, that does not seem to be too complicated. But I mean, maybe you agree this is a characterization, and maybe you say, okay, yeah, we've got Q equal to 2 figured out. But I mean, it certainly doesn't help me identify the graphs, right, that have this property. And then another observation that I'll put up here is just, it's one that's a little tool, I suppose, that if you happen to know Q is 2, then you can sort of start to figure out various patterns among, in this case, independent set, the patterns of neighbors and so forth. But I mean, this is just a little tool we use to, it basically says that if you have an independent set, then there has to be lots of common neighbors among the vertices in this independent set, roughly speaking. Okay. And as soon as you don't have enough common neighbors among a set of independent vertices, then there's no hope for Q to be 2. So just a little characterization. Okay, in that discrete math research group that I mentioned a couple times now in 2013, we did work out that Q of the hypercube was 2 for any n, right? But I do want to point out that actually what we proved was this inequality here concerning the Cartesian product of any graph when you sort of box it with K2, very straightforward Cartesian product. And so using this inequality, you just have to check that small hypercubes have the right value, and then you just keep iterating as you go forward. And I know my colleague Shala I know she spoke in this seminar or another seminar. She's mentioned a few times about how this result here, Q is 2. I just write as tied to the so-called sensitivity conjecture. She knows more about that than I do, but there is this connection that probably we should have been more aware of in 2013, but that's okay. But there is a relationship there. And I want to bring up a little remark that if you replace G by the complete graph, you get 2. Now, of course, that's boring because you guys already knew that. But what's interesting is there is a strong realization. So this is called the strong spectral property, which I'm not going to define for you today. But it turns out that once you have this concept of a strong realization with 2 distinct eigenvalues, then you can take any supergraph of this guy, and that has Q equal to 2. So that's just a little bit of a tasty treat out there, I guess, that if you happen to exhibit a graph that has Q equal to 2, and at the same time you exhibit the realization that it has this strong property, then you can start sprinkling edges in anywhere you want, and the graph still has Q equal to 2. I mean, you can take that as you wish, but I mean that is somewhat interesting. Okay, some other sporadic results. Here, if you take some sort of wild multipartite graph, you can detect when such a graph is 2, and basically it's just about lining up the parts in terms of the size. There's a little more to it than what we did a little more in that 19 article, but I mean, I'm just writing this down. You can take the complete graph and you can remove perfect matching, I guess I should say, maybe maximum matching or something here, assuming, well, we can imagine n is even and then we don't worry about it. this was done in a couple of places where, so you take the complete graph and you remove a few independent edges. You keep Q equals to 2, which is curious. You can do the same thing for the complete bipartite graph, as long as you're sort of careful. And there's a paper by Levine, Oblak, and Smigogic. In 2019, they looked at the complement of trees, and they showed that if you take the complement of a tree, that basically Q of those graphs are 2, except for a few sort of, you know, exceptional trees, but which they characterize. But on the other hand, you get this sense that almost all complements of trees have Q equal to 2. And then here, I'm not doing this work justice, because there is a lot of amazing work in this 22 paper that appeared by the same 3 folks. But I'm just writing here as a matter of being short with you folks, that the joins of unions of complete graphs have essentially been sorted out. And as I went through the paper to make sure I got it right, I think basically, you know, you take unions of complete graphs, you take joins of those things, you sort of, the Q value cannot be very large. And as far as I can tell, they've figured out when it's either 2 or 3. And that's really, truly an amazing result that they sorted out. And I do apologize that I should say things a little more carefully, but I just, for time, I just wrote it like this. But truly, if you have an opportunity to look at that 22 paper, there's a lot of great stuff in there. Okay, threshold graphs. So, excuse me, joins. I'm going to talk about joins. So you saw here that when you have the complete graph minus a few edges, you take the complement of a tree. Sometimes that looks like a join. The joins of unions of complete graphs, you know, that you see this sort of pattern emerging here, complete multipartite graphs, also a notion of join. And so it seems natural to consider joins. Furthermore, if you're studying this Q equal to 2 problem, you realize that, you know, if Q of a graph is going to be 2, the graph had better have, you know, a considerable number of edges. Now, maybe you argue with me and you say the hypercube does not have that many edges, and okay, maybe that's true. But generally speaking, when you're studying graphs that have Q equal to 2, you want to consider graphs that have lots of edges. And so the join is a very natural operation in that regard. And there's a cool little progression concerning the join. So in that 13 paper that I mentioned now a few times, we actually worked out that if you take a connected graph and you join it with itself, Q is 2. And that was really cool. We suspected that a lot more was true, but we didn't sort it out. Then later in 16, Montfort and Shader, making use of a really slick application of sort of having, so let me back up. So Montfort and Shader, in their work in 2016, the main result that they had in that paper was that if you're handed any connected graph and any list of n distinct numbers, you can realize those n distinct numbers as eigenvalues of a matrix from that graph, and all of the eigenvectors associated with those n distinct numbers are all totally non-zero. There's no zero coordinate in any such eigenvector. Then you can use an application of that result is this theorem. So if G and H are connected and they have the same order, the same number of vertices, then Q of their join is 2. I mean, it's sort of a dramatic extension of this result from 2013. You can push it a little further, that if the gap is at most 2, then you can still get 2. And that's about as best as you can hope for. And again, I love reading this result. I wrote this result out a few times over the weekend, trying to think of a way that I could say this. So here goes. In this paper in 2022 that I've mentioned now a couple times, this result appears, and this is truly a remarkable result. So first of all, it goes as follows. If you take 2 graphs, and as far as I know, they don't have to be connected, then the Q of their join is 2. if and only if they have what are called compatible multiplicity matrices. And I'm not going to define that for you folks here today. If you're interested and you want me to give you that reference, or you want to go look at that paper. But they basically they consider the sort of multiplicities of each of two matrices associated with these graphs, and then they have this condition that when these multiplicity matrices are called compatible. And so you might ask about the converse, right? Because this is like, okay, if the join has Q equal to 2, then you have this property about the two graphs. And they actually developed, sort of a, roughly speaking, a characterization of when Q in the join is 2. But their characterization is extremely, well, I should be careful. Their characterization is mildly complicated. So you see here, you have this concept of generic realizability. Okay, so that's a property. And then you have this other property called H is sane, which is like spectrally arbitrary, nowhere zero eigenvectors, right? With awesome acronym. I mean, that was really clever on their part. And once you have these two properties, then you can deduce that the graph will have the graph of the join will be 2, if and only if they have this compatibility multiplicity condition. So if you are truly interested in understanding when Q of the join is 2, then all you have to really do is go hunting for generically realizable graphs and sane graphs. That's all you really need to do, because the compatibility, then the compatibility multiplicity condition is exactly what you need, right? And later, you'll see a paper, I don't know if it's appeared yet or not, by the same three folks, where they talk about how paths are generically realizable, cliques are generically realizable, all these kind of things. So now they've started to just train of computing and checking when things are generically realizable. Okay, other results on the join. Now here's some consequences. Now this is not necessarily saying that the Q is 2, but in this case, when you take a graph and you join just a single vertex, you can predict what Q will be in that regard. And I mentioned joining with a single vertex only because it leads naturally into the next topic. So here is a result. It's written a little bit differently than just talking about Q of the graph. It's more about Q of a particular realization associated with the graph, but it does give you some interesting information. If you start with a graph and a matrix in that graph, and you hold in your hand an eigenvalue, and you happen to know that eigenvalue has an eigenvector where there are no zero coordinates in that eigenvector, then you can find a realization in the graph where you would join a single vertex and you join it to all the others, such that you can predict what will happen to Q of that realized matrix. It's either you add 1, you subtract 1, or you stay the same, and that depends on the nature of the eigenvalue you chose. And you can use this kind of result and other work that we did in this AIM ARC paper that's just recently appeared to work out what happens when you join a single vertex to a graph. And the hypercube was a curious example. You remember the hypercube had Q equal to 2, right? And so now you take a hypercube and you join a vertex on top of it. We were able to show that if you take the hypercube and join a vertex, then Q of the whatever results is never more than 3. And what was surprising to us is that Q can be 3. So you join a vertex on top, Q can go up, right? Strictly increase. And then it turns out that if you join one more vertex and you keep doing this, well, it turns out that there's this operation, if you will, called the join duplicating of a vertex. And it's been known, it was proved in 2 different papers that as you join more and more vertices, the Q value suddenly starts to be monotonic. And so the only real interesting case in this ball game here is to just join one vertex and see what happens, because after you keep joining more, the Q becomes monotonic. And of course, by the previous fact about the joins of 2 graphs, eventually, as you join enough vertices, Q goes down to 2. It must eventually get to 2 at some point, particularly if you start with a complete graph, I suppose. Threshold graphs, right. So threshold graphs, as I mentioned here, I'm not going to say a whole lot about them, but just a few little results. So threshold graphs are ones where you just have a bunch of vertices, And then you have this sequence where either you just join the vertex as a union, or you take this vertex and you join it to everything that's existing already. And you can build threshold graphs in this way. So either the new vertex is so-called isolated, or the new vertex is dominating as you sort of produce this sequence. Excuse me. And the trace of any threshold graph, capital T, is just that. So as you go through this sequence of vertices, and you either create an isolated vertex or you create a dominating vertex, you can create this binary sequence associated at the same time, where you put a 0 if the vertex is isolated and a 1 if the vertex is actually dominating. And so you can create this binary sequence, which is known as the creation sequence, for any, to any threshold graph, and vice versa. There is a correspondence. And the number of ones in any creation sequence is called the trace of that threshold graph. And in a recent paper with myself and my postdoc, we were able to work out, if you will, when Q of a threshold graph is 2. I mean, you might argue that the characterization is maybe as hard as the original problem, but anyways, it's something we can work out. This submatrix here that I've written, it's just the submatrix whose rows are indexed by the vertices that have 1s in the creation sequence, and the columns have 0s in the creation sequence. So this is like an off-diagonal block in that matrix A that you want to know is column orthogonal. And that's not a complicated result. If you start playing around with threshold graphs, you'll sort of see it. I mean, you got to sort it out, but you can sort out things fairly quickly. Now, once you know that, then you can start to write down some results. And so here's a condition where if you have a connected threshold graph and you happen to know Q is 2, then the trace has to be fairly large. Okay. And we have other results along these lines, and I'll just write down, so-called complete split graph statement, which is not much more than what I wrote up there, but nonetheless it says a little bit more than that. So if your creation sequence starts with a bunch of isolated vertices and then finishes with a bunch of dominating vertices, then you can predict what the Q value of that graph will be depending on the size of the sizes of the isolated versus dominating vertices. And it's interesting that in this case, Q is either 2 or 3, but maybe not surprising, but interesting. Okay, so moving on, we talked about joins, we talked about the diameter, we talked about other kinds of things. So what about if you impose regularity on the graph, right? Because this is the natural progression. If I can't solve the problem in general, I impose conditions on the graphs, and maybe I can then learn something, like if it's a join, if it's this or if it's that. And so recently in another AIM ARC group that I've just labeled as Q/Q, we were able to characterize regular graphs up to degree 4 that have Q equal to 2. And here they are for when the regularity is at most 3. Here are all the graphs that have Q equal to 2 when you require the graph to be R regular. And I just mentioned a little lemma in the middle of that paper concerning the Cartesian product of cliques. You'll remember I talked about the hypercube and the Cartesian product when you take K2, right? And something kind of pretty happens with K2. When you move beyond K2, well, okay, it gets more complicated, obviously. And in the case of Cartesian products of 2 cliques, we were able to sort of work out what Q looks like in that regard. And this lemma played a role, as you can see up top here. This lemma played a role in sort of ruling out graphs that didn't have Q equal to 2. So you might ask yourself, okay, so that's R at most 3. What happens for R is 4? This is what happens. It gets rather hairy. So if you have a 4 regular connected graph and you impose the condition that Q equals 2, then here are all the graphs that have Q equal to 2. And I didn't have the wherewithal or the ability to write down all of the other sporadic graphs. The only one that I chose to write down is something we labeled as the closed candle, and this is one such closed candle up here that you have. And then there's there truly are kind of sporadic other 4 regular graphs in the paper. You can see them; they're all sorted out. But the upshot of this result is first of all that it was a testament to the energy of the group to sort of get it solved. But second of all, it's becoming more clear now that, you know, if you wish to go to the 5 regular case, I mean, you really have to roll up your sleeves. I mean, it's going to get, you know, there'll be a lot of interesting classes that kind of reappear, but I think it's going to get rather hairy as you move forward. So what if you ask yourself, okay, suppose instead of just being regular, what if I'm strongly regular? Well, the cool thing about strongly regular graphs is that, you know, for eternity, it's known that the adjacency matrix of a strongly regular graph has 3 eigenvalues, which means that the minimum number of distinct eigenvalues across a graph that's strongly regular is at most 3, right? So it's either 2 or 3, you know, unless I'm the empty graph. And okay, now before someone yells at me about what is mu is the parameter associated with the non-adjacent vertices, right? So every pair of non-adjacent vertices has to have a mu common neighbors. And you can, you know, just using basic rigmarole associated with strongly regular graphs, if mu is 0, you can decide that q is 2 and so is the complement. If mu is 1, then q can't be 2, and that's just a consequence of the neighbor condition that I was just discussing before. And I guess for a while, you know, kind of between me and my blackboard, I had this kind of idea that the graphs in bullet 2 were the only strongly irregular graphs that had q equal to 2. And then, of course, very quickly, someone told me, no, that's not right, because the line graph of the complete graph has q equal to 2, and it's not of bullet number 2 type. And that's done in this paper here by First and Grutz, where they looked at so-called tight frames is what they were looking at. And so I'll just go ahead and say it out loud then. You know, maybe characterizing the strongly regular graphs with q equal to 2 is interesting. I mean, perhaps if folks are into strongly regular graphs, that's something you could certainly consider. And as far as I know, you know, that's not been completely resolved. Lastly, this group that I referred to here, the AIM ARC group, we asked another kind of question where we said, you know, okay, suppose you're handed the number of vertices of a connected graph. So you know you're assuming the graph is connected, you know that the number of vertices is n, and you impose the condition that the graph must have q equal to 2. That is, there is a realization A that has only 2 eigenvalues. What are the fewest number of edges that could exist in that connected graph, right? You know, natural question. And as I've kind of hinted before, right? It seems plausible that if you require q to be 2, or if you want q to be 2, then there needs to be a lot of edges. Of course, there are exceptions to that, as you'll see here below. So we worked out a theorem that, depending on whether n is even or odd, that if you only ask about the number of vertices, connectedness, and q equal to 2, then the graph you're holding in your hand has to have at least this many edges, either 2n minus 4 or 2n minus 3. And furthermore, we actually worked out what are the graphs at the extreme situation, so that, you know, actually equality may hold. And one of them is the hypercube. You know, it depends on whether n is even or odd. You get the hypercube popping out, and then you get these two graphs here, the so-called, if I got this right, the double-ended candle and the single-ended candle, as we named them here. I'll just mention quickly in passing, there's sort of a complementary problem you might ask about graphs that require q equal to 2. And so this is, instead of asking about the fewest number of edges, now you ask about, starting with the complete graph and you remove some edges, how many edges can you remove and keep q equal to 2? And that's work that's currently ongoing with this same AIM ARC group. Okay, I am close to being finished. Obviously, the question of the day is to, you know, someone please sort out the graphs that have q equal to 2, so I can move on to something else, I suppose. You know, I'll leave you with this sort of passing comment. The following fact is true after this column. I mean, every graph is an induced subgraph of a graph that admits an orthogonal matrix. I'll leave it at that. And maybe you find that interesting. Maybe you after you think about that statement for a moment, you realize, okay, the characterizing the graphs that have q equal to 2 is going to be really hard. I mean, for example, going by simply induced subgraphs is not going to be particularly useful. I still want to do more work with eigenvectors. I mean, I'm not quite sure how I'm going to do all that, but I gave you a hint with regard to the bordering group paper that eigenvectors did come up, right? The totally non-zero condition on an eigenvector that did play a role, and there's going to be more to it than just studying the patterns of eigenvectors. I think there's more to it. I've gone back with my other PIMS postdoc Pratik, and we're going back to the bipartite case where, for the bipartite case, when you insist q equals to 2, there's a lot of there's work that's been done already, and we're not so much interested in just bipartite with q equal to 2, but what if you're bipartite with q equal to 2, and what else can you sort of do so that you can keep you can add edges to the graph in a way that you keep track of the q value. That's kind of what we're doing, and we're making progress. I don't know what the T is there. Sorry. And so naturally, restricting your graph to have other kinds of properties makes a lot of sense, I suppose. I mentioned the open problem associated with strongly irregular graphs, and of course, you don't have to just mess around with those. You can talk about distance regular graphs if you want. I mean, there's other kinds of properties as well. All right, folks. There's a number of projects that I sort of highlighted here as I went along. I talked about work with my postdoc, Saeed Mojahali. There was the University of Regina Discrete Math Research Group, actually 2 editions of that group, 13 and 19. The American Institute of Mathematics have developed a virtual research community on the inverse eigenvalue problem of a graph. That was sort of born out of the pandemic, I suppose. And I've been a part of a few projects there, and 3 of them I mentioned in this work here: the bordering group, so-called, and then the QQ group, where I referred to 2 separate projects from that. I also made reference to a group that I worked with, which was originally an AIM Square in 09 and 10, that became a BIRDS focused research group later on. So Sabrina invited me to speak. Maria has been moderating the session. Thank you very much for inviting me and taking the time to help me out with this seminar. And of course, to all you folks for taking your time to listen to me yabber on. I appreciate it. Thanks, guys. Good.
Okay, yeah. Thank you for your talk. It was very interesting. And
Okay,
are there any questions for Shaun? Yeah. Okay, Jane has a question.
Hi, Shaun. Thanks for your talk. I have a question that might be dumb. That's okay though. So you mentioned that there was this condition on the neighborhoods of vertices in an independent set.
Right.
Is it at all helpful to like as a sub problem of the greater problem to look at like a fixed independence number and see what values of Q of G are possible for that, or if that gives you different bounds on things? Or are there too many examples where the behavior kind of varies between different?
Okay, the short answer is yeah, why not? I mean, I can sort of give you the proof of that neighborhood condition. So, okay, why did we insist on the subset being independent? Okay, so if you look at the diagonal block associated with those vertices, if it's an independent set, then I gave it away. If you look at the block associated with that independent set, it has to be a diagonal block.
Right? Yeah.
Okay. And now what you say is, oh, I want that matrix to be orthogonal, which means I want those rows to be orthogonal. Well,
of course, yeah.
Then what you do is you look at the other block where you look at the neighbors of those independent vertices, and you need those things to all be orthogonal. And then we kind of worked out the most, the sort of obvious pattern that you need to sort of work that out. So I suppose the answer to your question is you could start there, right? And you can look, but but we did we did like the degree 1 case, right? Where you just looked at the pattern and what you need to ensure things to be orthogonal. And the answer is, that block, that off diagonal block cannot be too rectangular is what we were kind of saying, right? That's all we were saying. But
okay.
You know what? It's not a dumb question at all. I mean, I'm kind of at my wit's end, so I'm willing to sort of take any result you can. So if you want to impose it on the independence number, go for it.
Cheers.
Yeah, cheers. Yeah, thank you.